Welcome back. Today I will talk about exploring data, which is a part of lecture 2. In many textbooks and also many courses, the part of exploring data is very often overlooked. I have reviewed so many textbooks, in particular in econometrics, where you go straight into some fancy equations and regression modeling without actually looking at your data, without exploring your data first. I believe this is a massive mistake. In practice, data exploration is absolutely essential. It's very likely that your data has some problems. So, for instance, if you do a survey, it's quite possible that coding mistakes happen. Yeah? So you provide some labels maybe, and you're mislabeling, and mistakes happen. Also, when you work with very large data sets, again, it's very likely you have what you call outliers. You have a few extreme observations. Sometimes these observations, they are actually correct, so they have been observed, they are just a bit unusual and you have to try to explain them, but very frequently they are also the result of some mistakes in databases. So, in my opinion, it's absolutely vital before you do any further modeling to look at your data, to explore your data, to see are there any issues that might cause problems later. You cannot fix really poor data quality in a straightforward manner. It's absolutely essential to check your data first. Now, what we tend to do not only in research reports is we tend to report what is called descriptive statistics. So when you write reports, you provide a summary of your data set. You give some basic information about the size of your data set, the outcomes you observe, and for that having a descriptive table is absolutely essential. So the main points you would like to capture are what is the average value of your variable, which you call the mean. What is the median value? Yeah, so what if you rank your observations and you go to the middle one, that's the median. So what's the value of the person in the middle? What if mean and median are very different? This tells you a lot about the shape of the distribution. We actually will encounter this in this session in the case of income distribution. Then we look at the standard deviation, or the variance, which is the square root of the standard deviation, which is a measure of dispersion. So how far away from the center of the distribution are you? So how how flat, so to speak, is the distribution? Very often I also report the minimum maximum value. Again, it gives you an idea about the range of your variables. It can give you some ideas also about outliers. So sometimes, for instance, negative values do not actually make sense, but you still might find them in your data set. So looking at the minimum value and seeing a negative value that shouldn't be there is a good starting point then to investigate are there any issues in your data set. We also look at percentiles, so this is basically different parts of your distribution. They can also be used very effectively in modeling. So, in my opinion, this is the best starting point for any further analysis. Look at your data, explore your data, do some box standard descriptive statistics and see what happens. Do you see anything unusual? Now, I just show you here an example based on the UK household survey. This is a spending survey, which you also find on GitHub. This is a slightly older version, but you get always the up-to-date version from the Office for National Statistics if you want. And this is quite a large data set that explores households' income levels and spending behavior. So in this table, what we see is we have two variables, size, which refers to household size, and income, which is a weekly income measure. We see the number of observations, we see the average, the mean, the standard deviation, minimum and maximum. And it gives you a sense about how these different variables are distributed. And we will see this now in a minute. So I will now switch into Stata. Actually for the rest of this session, so I'm playing a bit in Stata. Again, you have the slides for further guidance, which are on GitHub. And let me just open now the data set. The data set is available on GitHub, as I mentioned. You can just open that, and initially it will pretty much overwhelm you. It's an awful lot of variables, lots and lots of them. The first thing I want you to do is, once you opened it, just save it somewhere, and again we go straight into a Stata do file. You remember how to open the do file, you just click up here. So now we are in the do file, and here we call this maybe exploration, or yeah, let's just call this exploration. Yeah, let's call this exploration. I will just save that straight away in this one, and I call this yeah, maybe data exploration, yeah, something like that. Let's do that. And the first thing I do is I change my directory using the path provided. I have to cut off the last bit here because that's my file name. So that's quite a good start. I should be careful with my quotation marks, and I have here the use command. I just drag this below. So a cd, as we have seen in the previous lecture, is change directory. I go into my path. This will be of course different in your case wherever you want to save it. So this is now my working directory. Then I open the data set. So you open the data, and we use the option clear, which clears data in memory. So we are all set. Yes, if we run this now, that, fingers crossed, should do it, and it reopens the data set. So it's all nice and clean. I always prefer working in the do file, because if anything happens, I can always go back to my original data. So never ever change your original data. Yeah, if you want to make changes to your data set, of course you can do that, but always save this as a new modified data and always provide comments what you have done. The most important thing is you have to be able to replicate your analysis. This is absolutely essential wherever you work, in any professional setting. If you can't replicate what you have done, this is a very bad sign. Alright, good, so we have done that. I just again zoom this a little bit so make it easier for you to see that, and also for me, given my advanced age and of course too much screen time. So now we are actually ready to go. The trouble with very big data sets is you don't know where to start. So for instance, if you now want to look for income, you have all these different codes. You don't know which of them is actually income. Yeah, no idea. The first thing I want you to try when you don't know a data set is to use the DES command. Yeah, this means describe, and this gives you the variable name, the type, the format, so how you display the different values, and potentially some value labels if they are available, and then you have the actual labels. So this gives you the details about the dataset. Of course, now you can look through all of that and hopefully you find, for instance, household income, but that can take a fair amount of time because this goes on, it goes on for quite a while. So it's useful to look for a specific term. Look for is the command to do this. So you just type in look for, and for instance, if you want to look at household size, let's just type in look for size. And here we are. So we have a variable name which is coded as A049, which is the household size. Now that's not a great name. Yeah, so it would be a bit confusing. So let me just take that. We go into the do file, and I just do here a section on renaming. Yeah, so I just make a comment. I want to rename a few things. Otherwise I have no idea what that means. I always have to check then the description, and that takes too much energy, so I just rename it. So when you rename is another command which is very useful. You start with your original name, and then you put in the new name, and that's all you do. So this will rename my variable. It maintains the same label, so the label is not affected by that. So that's a good start. Okay, the next thing I need in this case, we can just now mark this and run. So it should work. It does actually work, and we should oh, I did put in, which is stupid, income. I was too quick. It should be size. And the good thing about a do file is I can now just run it one more time, and it's all fine. Yeah, so it should be size. Yeah, so that's good. Of course, there's so many in here, so we have to maybe change the order and move size first. We can do this, and now you see size is popping up here, top of the list. So order is just changing the order of your variables. Sometimes useful if you have so many variables here, so we can just say change order of variables. So that will do it. Now I was a bit too quick about this. I can also maybe throw in the look for command here. It's just nice to have it in one place. We do another look for. In this case I want to look at income, and there are, I warned you, many income measures. And now you have to know a bit more about surveys. I don't want to really cover it, except you really want me to. If you want, just leave a comment down below. There is a lot to say about household surveys. I have worked on them not only for the UK, but actually mostly for China. I also did a paper on household surveys in China. Very exciting stuff. Now the one which I tend to use, again it's debatable, there are different ways of adjustment, is this one here, which is the income for the household which has been adjusted for household size. There are different ways of adjustment. So if you just Google this, equivalence and OECD scales, so you will find documentation for how this is done if you're really interested. For us now at this point it doesn't matter, we just want to explore the data. So we just take that and we rename this, and we just call this now income. So we have our income measure, so that's pretty good. Okay. We can change the order. We put size first, income next, so that's all done. And now we just do some standard descriptive statistics. So let's do this, descriptive. So the command for that is simply sum for summarize, and I throw in income and I throw in size. And that gives me a table of some descriptive statistics, and here we are. So we get observation, we just saw this before on the slide, the mean, standard deviation, minimum, maximum. So that's quite useful. So that's a good start. It's quite often not necessarily what I want. Quite often I want to have a bit more information. I want to look at more of the distribution of it. So what I tend to do next is I tend to use another summarize command, but put an option for a particular variable. So for instance, I do the following: I do summarize for income, then I use the option introduced by the comma, and I do detail, which gives me a more detailed discussion about this particular variable. So it goes into all sorts of measures. Now you get an awful lot of information. You get the different percentiles. So this is basically the distribution cut at different parts. The 50%, so that is your median. Yes, if you look at this median here compared to the mean, you know that the median is obviously below the mean, which already tells you that the mean is influenced by a few very, very large observations. The median by construction, because it's the person in the middle that determines the median, is not influenced by very, very rich households. The mean is influenced by that. So looking at average income is not a fantastic measure, because one big outlier, so Ellen for instance, a massive outlier, is driving this up quite a bit. There is a little restriction to what I said in place here, because in the case of a household survey in the UK, household income is capped at about £2,000 a week. So if you earn more than £2,000 a week, which almost none of us actually do, then you are capped at 2,000, and you will see this in the distribution in a minute. You get some more information here. You get the variance, which is simply the square root of the standard deviation. So it's a measure of dispersion. So how far away are you from the center of the distribution? Then you get the skewness. The skewness is positive in this case. A positive skewness means that you have more extreme observations on the right hand side of your distribution. So in this case it means you have a few very large incomes that skew the distribution to the right. So it's a right skewed distribution. And you see this when we look at the distribution in a minute, that it's a bit moving to the right because of these very large incomes. Then you have the kurtosis. Kurtosis is a measure of what happens at the extremes, both ends. The very small observations and the very, very large values. That's the kurtosis. A value above 4 would indicate you have what is called a fat tail. So a fat tail means you have observations that are either very, very small or very, very large. Okay. Again, this is very, very typical in certain circumstances, in particular when you explore financial data. So if you go into data, say stock returns, you will see something very similar. Good. The next thing I want to do is to look at distributions, and the favorite I use is a histogram. We can also do something else, and it gives you another way to visualize what is going on. So here we look at his histogram, so we look at the distribution of your particular variables. So for instance, we do here a histogram, if I spell it correctly, and we focus here on income. Let's just maybe do that first and see what happens. And yeah, here you are. And actually it's quite nice because you see exactly in the histogram what I spoke about before. You see this bulked up figure here. And this is due to the fact that incomes are capped. So at one point you cut it off. This is of course already a modified version of income, adjusting for the size of households. So at one point you are simply richer than the top level. So you already have here a cut-off distribution. But definitely what you observe is that it is a skewed distribution. It's skewed to the right. It has a positive skew, so it's not very much symmetric. So that is interesting. It simply, of course, indicates income inequality, which is not a big surprise. So that's quite a nice figure. What I also tend to like is another way to visualize it, using a so-called kernel density, so key density income, which is just a little bit smoother, does the same. You can also make lots of adjustments to it, but we don't necessarily have to do this. So that's another version of it. If you want to compare these to a normal distribution, you can just use the option normal. And obviously you see what we already know, that it's not at all looking very normal, because you clearly have a skewed distribution. You have a few very large outliers. Yeah, so that's quite useful. Good. So we have done that. We looked at the distribution in this case. We looked at how this shapes up. The next thing what I quite like, in particular when I work on household data, is I want to explore, for instance, income for different types or different groups. Yeah. So groups or different types of people. And I want to use that then to, talk about some, for instance, policy issues, or talk about the impact of taxes on certain groups and so on. Okay. Now, very often when it comes to groups, you would define groups by age. Age is a very important predictor when it comes to household size, when it comes to income, types of income, and so on. So let me have a look at age. Let me do another look for, and of course now here we will get lots of stuff, because age is a key indicator. So we get a whole bunch of things. In particular, what I want to do is now I want to look at older people. So we look at this category here, and this gives you adults over the age of 70. So that is an indication, the number of adults over the age of 70, that you have older people in your household. Yeah, and of course now we can discuss what's the right definition for it, how many do you have and so on. But let me just have a look at this variable here. I just break that now for a sec, and I just rename it first, and I just call this older. Maybe you shouldn't do this anymore. Yeah, but it's you can't say it's middle-aged. I wish. Here we go. So now we have older. It might be nice just to have a little look how older looks like. It's funny to say that. What we actually have in here. So this is a measure of the number of older people in households. It goes up to 3, yeah, but it doesn't seem to be the most likely outcome. So looking at that, there are lots of zeros in here. So it depends now, of course, how we want to define things. Yeah. So we could, for instance, define a household which is maybe a household with older people as one that has at least one older person. Yeah, but that's a matter of definition. For our purpose here, we just explore the data structure. It doesn't really matter. So this is actually something you have to think about when you analyze this problem. So let me just say we do the definition that, let's do that we generate. We could generate a so-called dummy variable. So a dummy variable takes the value 1 if a certain condition is met and value 0 otherwise. So I do a dummy for older. So I just use here d_older. And I define it in a certain way. So the generate command generates now a new variable. Yeah. So what I do here is I generate so-called dummy variable using the generate command. I call this d_older, and now I have to say how I do it. I just say, okay, I assign the value 1 if a certain condition applies, if my older value is at least, so is larger or equal to 1. I could do something like that. Yeah, so we could run something like that, for instance. Let's just do that. Okay, let's do that and have a little look. And now we just want to check out older and d_older and just see what happens here. So you see now we have lots of missing values generated because this condition is not always met. Now the moment if we use this statement, if you just read this out, it gives the following instruction: assign the value 1 to the new variable d_older if older, which is an existing variable, is larger or equal to 1. It doesn't tell me what happens if the condition is not met. So what happens is only ones are generated for these particular cases. Yeah, so if we now look at the data doing a browse command and we only zoom into older and d_older, we can just see what happens. Yeah, so this older here, this would be a 1, which means there's one person which is old in the household, so it would label as 1, which is correct. Here is no person in the household, so the if condition is not met, and so it would generate a missing because it doesn't know what to do, because he didn't tell what to do. Yeah, so we generate here missing values. If you go to 2 older people, again it's more than 1, it's 1. Again, there is no older person, so it doesn't know what to do because the if statement only specified what happens if the condition is met. The condition is not met and you don't know what to do, so Stata assigns a missing value. So a dot in Stata indicates a missing value. So now how to change these missing values, because you actually want a 0 assigned if the condition is not met. There are different ways to do these things. One way is to use a replace command. Another one which is useful to learn. So d_older is equal to 0. And again I say now, well, if d_older is actually missing, yeah, equal to dot. So that is a very common way to specify if conditions with equality. You do a double equal to sign. So in many programming languages, assigning a value is done using one equal to sign, and assigning having a certain condition which depends on a certain value, you use the double equal to sign. Now this is true for many languages, and also it happens here in Stata. Now this should do it. Let me just run this and check again what happens. So now you see wherever there was a missing value, there's now a 0. So now you have actually a nice label where I only distinguish between do you have at least one older person or not. So it's a 1 or a 0. So that's quite nice. So that's a useful starting point. Whenever you generate a new variable, it's useful to label it, because I promise you after a week or two you have no idea what it really means, and you have to otherwise go back into your do file. So I put in label var, which is the command for providing a label for your variable, and d_older, and then I assign a string to this using quotation marks, and I just say here this is a dummy that takes value 1 if at least one person in household is 70 plus, and 0 otherwise. I don't have to say that, well, it's a dummy variable. So that assigns the label. So that's useful. So whenever you now do a describe on this particular variable, you see what is labeled. So if anyone works on your data, does a normal describe command, this description would tell this person, okay, this is what it means. And I think this is really a really good idea. Yeah. Good. Okay. Right. So that's a good starting point. Let me now think about some other ways of visualization. So what I quite like is I quite like to compare, for instance, income across groups. Yeah, so we can do this exercise. There are many different ways of doing this. What I quite like is to use a so-called box plot. So let me just do this here, box plot. The command is graph box, and then the variable you want to look at, we want to look at income, and then we want to look at this for different types. And now I do here the by, and I refer to d_older, and that should do it. I just run this now. That might take a while. Here we go. So now you also see that the label is displayed here below. All of these things, they can be modified. Of course, you can modify the labels. You can actually quite nicely export your graph as well. You can save it, you can export it, you can start editing directly here. All of that we will talk about in future sessions a bit more. Again, if you have any questions or you want to explore this further, just leave a comment below. There's a lot to say about visualization in Stata. Now, the box plot gives you a comparison of the distribution of household income for the households that don't have older people and the ones that do. Yeah, that's actually very interesting. So of course, in most cases, we haven't checked this carefully. The households that have older people, these households are mostly in retirement, so they tend to have lower incomes. But you see lots and lots of outliers for higher levels of income. But the distribution is a bit squeezed to the lower level in this particular case. Now the box plot is can be read as follows. You have this line here in the middle. That's your median. So that's the median, and you can compare directly with the households with older people. You see that the median level of income is definitely lower in the case of older people. And then you have this line here, which is the bottom 25%. And that line here is the bottom 5%. So here you basically have zero income levels. And interestingly, when it comes to the bottom, at least, you have higher values for households with older people. Then on the top end, you have a top 5% level, which is a massive difference in terms of income. And then all these dots here are outliers, again indicating a positive skew in the distribution. So that's a very nice way to visualize income levels or any variable for different subgroups. Yes, this is one of my favorite things to do. Good, so now we explored quite a few issues. Visualization, I think, is nice and important, and again this could end up in your report or in your dissertation or anything you want to do. Let me just pop back into the slides just to make sure I'm not skipping over important issues. I have done this here in a slightly different way, but it doesn't really matter. It's up to you. Well, I want to talk a bit more about missing values and outliers. Now, well, missing values are very, very common, in particular when you work with large data. In the case of surveys, for instance, some household might not respond, so you have all sorts of potential biases that might be caused by it. In most cases, it's not a massive problem. If you have a sufficient number of observations, it's not necessarily a massive problem for your estimation, but of course you create certain biases. So for instance, in the case of surveys, you have the non-response bias. That's it's a tricky one to address. it can be addressed to some extent, but this is something really for another session. Again, if you want to know more about these things, just leave a comment below, because this really goes then very much into issues around sampling and adjusting for biases, which is exciting but rather complicated. So in most cases I wouldn't be too concerned about missing values. However, different disciplines handle missing values differently. So if you are working more in biostatistics or in medical research, they tend to try to fill in the gaps, and there are different ways of doing this. So what they do is they use the observations you do have to predict missing values, so kind of filling in the blanks. So this is quite a common approach in certain areas. In other areas this is not at all common. So it depends a bit on where you are with your kind of work. Outliers, again, it's a bit difficult across the disciplines. They view things a bit differently. I personally I'm very reluctant to just remove outliers, because in to some extent, of course, you can do this and you affect your outcome. So if you want to push, for instance, for a certain agenda by removing what you don't like, you of course get there. So I'm not a big fan of that. I usually prefer to keep everything in the data set, and then, you know, describe and discuss why there are certain outliers. There might be good reasons for it. Sometimes it's simply mistaken the data. Also, quite often you can use better methods to address outlier issues. Yeah, so there are problems if you go for a standard, for instance, regression model, and we talk about this in the next lecture in more detail. But in most cases you can actually adjust your modeling to account for outliers, or you do what is called a Winsorization, which in certain disciplines is very common, in others not at all common. So that's the interesting thing. I will talk about Winsorization and how to implement this in a minute. But of course the big question is, you know, should you do anything about this? And I think there is no particular I would say recommendation, and depends very much on the discipline. So I'm more of the opinion that I would report outliers. I would discuss that. Sometimes if I have to take action, I can do it with more robust methods. One example would be quantile regressions. As we already saw, when you look at the median is not bothered with outliers too much. The mean is. So if you use so-called quantile regressions, you can actually get rid or mitigate the impact of outliers. It doesn't do everything, but it does it to a large extent. I don't explicitly cover quantile regressions in this beginner's course, but again, if you want some material on that, I have plenty. I worked on quantile regressions, and also quite a few co-authors of mine did so. The other thing I like to do is I like to compare. So I like to run my models, including, excluding outliers, and just see what happens. And in most cases, nothing happens. It looks totally fine. It's very similar. It's qualitatively the same, so I wouldn't be too concerned. However, if I see that outliers really totally change the picture, that would be definitely a matter of concern. And again, this is why it's so important to explore your data. Now, the other idea, and this is really common, in particular in the management business literature, is to use what is called Winsorization. So Winsorization applies a cap, so to speak. So you look at the bottom and the top of your distribution, and you simply cut them off. So if you have a value below the lowest percentile, which you define maybe at 1 or maybe 5%, you replace that value with the respective percentile. The same you do for the top end of the distribution. So this is used a lot in applied work. It's not perfect. There are issues with it. And here it is an example of how to do it, and I will just show you this in a minute in Stata. Let me just stress one point. As long as you are transparent and you say what you do and you explain why you do it and you show me what happens with and without the adjustment, I think this is perfectly acceptable. It becomes, of course, more problematic if people are not very transparent and they don't, for instance, discuss any adjustments of data. I think then it becomes problematic. Good. Let's have a look and go back to Stata and think about these adjustments and try to implement that. There is already a built-in visualization command. So if you want to look for some new commands in Stata, you just go to Help and you go to Search. If you know the command, you can just go straight to Stata command. If you don't know, just go to Search. And you put in here, for instance, visualization. Might have a different spelling. Yeah, might have a different spelling. So you have to try this. I think it might be maybe also under Winsor. Let me see. Let's try this. Okay, here we are. Here we are. That's right. So that's Winsor. That's Winsorize variable. So this is already a built-in command. It was written by a user. Honestly, you can do it yourself. Yeah. So that's the thing about Stata. People can write code. They can make it available to other people. You can just click on this, install it. Yeah. Again, if you are, if you have control over your computer, there's no firewall, nothing, and so on. Otherwise, you might sometimes have issues. I worked with HMRC, and they could not do anything because of, very powerful firewall, and they couldn't install anything from the internet, basically. So this makes it quite more difficult. You can also look at the so-called ADU files online, and you can download them and run them yourself. That's another way of installing. Again, if you have any questions, just leave a comment below, and in most cases this can be sorted quite nicely. I personally write my own code. I don't like to use other people's stuff, except I'm a little bit too lazy. But the good thing about writing your own code is you learn more, and this is also what we anyway want to do here. So visualization. Here we are. So how do we, now I spell it differently anyway. How do we do it? Okay, so first of all, let's just talk about what we want to do. Let's focus on income, for instance. So what we want to do is we want to get into the percentile of it. Yeah, and you see this in here. This is what we do in this first part. Yeah, I'm a bit lazy now. I just copy paste that. You can also do exactly the same. So the thing you notice here, before we use the generate command to generate our dummy variable. Yeah, so this one here. And then we replaced values. Now we use egen instead of generate. Egen is basically a command which can be extended by the user. So you could write your own code, you can modify things, and so on. That's the only difference as far as I'm aware of. Now what I use here is the built-in imegen function, and I just show you that. So you go to help, you go to Stata command, you type in egen, and here are all the things you can do with it, and it's quite a lot. You just have to explore this in your free time. It's highly entertaining. And somewhere in here, I believe there are the PC tile. So this is the percentile, and you see the syntax. It allows P as the option for the percentile to specify. And this is exactly what we have. So when we go back in here, we have PC tile. I refer to income, so that's the variable I want. I go to the bottom 5%. I do now the same for the top 5%. Yeah, there would be 95 here and 95 there. So that should give me the bottom and top of the distribution. So if I run this and if I have a little look, that should be fine. If I do now a summarize command, I just want to have a little look whether it kind of makes sense. We see that that's the bottom one is £100, that makes sense, and the top one, you see all the same values, is £1,000. So if you put differently, if you earn more than £1,000, again this is adjusted for household size, per week, you are in the top 5% of earners in the UK. Yeah, so that's quite interesting to know that. Good. Okay. Great. So that's it. So now in terms of adjustment, what do? So we create maybe a new variable. Again, this you can also override the old one, but I think it's better you do something new. So we just say a generate command, and we do a W in front for visualization underscore, and then we say income. And in fact, I just take the same value as long as I'm inside the bottom 5 and the top 5%. So I say I generate a new variable called W underscore income, which is equal to the original variable if income is in a certain range. So if income is larger than the P5, and so there are two conditions now, income is less than P95. And so that's basically what I do. So I cut out the rest, and we will just see the impact in a minute. Now if I do a two-way chart, and I throw this actually into the do file, so if I want to two-way charts, which is quite nice. So two-way charts combine different charts into one. So it's a bit like, when you do Python, it's like, having a so-called subplot. So this is a different command for that. So two-way, and in brackets you specify the first one and the second one. And we can do this using k-density. So we have done this before. So these kernel densities, the distribution, if I can spell it today, income. And we do the same for the visualization. We can just have a look at this now after the first modification. Let's just run this, and you see that you cut off, you see that, so here you cut off the top and you cut off the bottom, and of course this is affecting your distribution. Again, that's a kernel density. The histogram would look a little bit different, but they would actually totally overlap. You might not see that much. Good. The next thing I do is I replace now certain values. So what I do is I replace W income with the P5, so with the value of the percentile at the bottom 5% of the distribution, if income is below or equal to P5. Well, this equal to we include this. That's the right thing to do. Good. We do something similar at the top, so we replace the income value with the top 95% percentile if we are larger or equal to 95. So we adjust that. Let's run this, and let's have another look at our chart. And now you see this funny thing happening here. So it looks a bit like a butterfly, and this is very typical for visualization. So you cut off all the tail, and all these values are reallocated to the value of a percentile. You see this also quite nicely if you do this in the histogram. It's maybe even better here. Okay, here we go. Here you see that, yeah. We should maybe change, here the colors, but you see basically the effect of cutting off and changing the values. And this is actually the effect of visualization. Good, so now we explored data. We have done an awful lot. You see in the slides there's one more little chapter on tables. I think I would put this into a separate video on tables, because in many cases it might maybe not interest you that much, depending on the type of work you do. So I see you in the next one.